Hello, so today I'm going to be showing you how to solve a new Sudoku I've created, which is called Diagonal XV. It's a very creative title. Continuing in my series of taking standard constraints and making them diagonal, thus making them non-standard. So this is combined with Kropki dots because XV by itself cannot differentiate between 1, 2, 3, 4s very easily, well, at all, without giving givens, and I seem to dislike givens in my puzzles. So we have Kropki dots instead. It makes for a very interesting solve. So I'm going to go over the rules. So the most important rule is the Diagonal XV rule. So of course we have normal Sudoku rules, but also you'll see we have a V here and then a bunch of X's, and they're at intersections. So just like my other diagonal puzzles, in case you've tried those, the digits that are diagonally adjacent to each other, that see an X or that see a V, must sum to a certain amount. So if they see a V, they must sum to 5. You can remember that because V is 5 in Roman numerals. And if they're separated by an X, they must sum to 10, just like X in Roman numerals. So these two have to sum to 10, these two have to sum to 10, these two have to sum to 5, these two have to sum to 5. Now, something I do want to point out is, unlike normal XV, where it's adjacent digits, with diagonal XV, it is absolutely possible for it to get 5 plus 5 equals 10. So please don't forget that. And that also applies for the negative constraint on this. So you didn't think there was just a positive constraint, not in my puzzles. So the negative constraint says that if there isn't an X or a V between two diagonal cells, then they cannot sum to 10 or 5. So for example, these two can't be 4, 6 like this because that adds to 10, and they can't be 4, 1 because that adds to 5. So that's the XV rules. The other rule is standard Kropki dots without negative constraint. So between two, if there's a white dot separating two cells, and it's always going to be adjacent cells in this case, a white dot means that they have to be consecutive. So if I were to put a 2 here, then this would have to be a 1 or a 3. I couldn't put a 4 because that's not consecutive. And F puzzles, unlike the diagonal constraint, F puzzles will helpfully mark that red if you get it wrong. And then for a black dot, they have to have a ratio of 1 to 2. So whichever one is smaller, the other one is twice that. So we can have 2, 4, for example. But we could also have 2, 1 because 2 is twice 1. So you just take whichever one's smaller, you double it, and that has to be what the other one is. And that's to cross black dots here, 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 here. So there's no negative constraint for the Kropki rules. So it's absolutely possible for us to do 1, 2 here. That's allowed. We can do 2, 4. We can do 2, 3, all of that's allowed. There's no negative constraint on the Kropki, just on the XV. So don't get that confused. And so those are the rules. Feel free to give it a try in the link below. You will see a page just like this one, and you'll be able to try to solve it. And if you don't want to solve it, or if you get stuck, feel free to just watch my solve. All right, I am going to get started. So I think the best place to get started is to first examine this cluster of dots and the V here. So if you've ever done an XV before, it should be immediately obvious that on the V, we're limited to 1, 2, 3, 4. Because if we put 5 or more in a cell, there's no way it's going to add to 5. Because you can't put a 0 in the cell or a -1, right? So 1, 2, 3, 4 is here. But if you also know Kropki, black dots, it should be obvious that we can't have a 3 here because the only thing that can go with 3 against a Kropki black dot is a 6, and we know we can't put a 6 here. So these can't be 3. So now when we have a selection like this, we can just look at the ones next to it. And we're not doing adjacent, we're doing diagonals. But because these two are the same, we can just look at the diagonals as, okay, what can be diagonal with a 1, 2, 4 to add to 5? That means we need to remove the 2 from this side. So next, we'll look at these white dots here. And if you look carefully, you can see that this can't be a 4. These two can't be 4 because they have to be consecutive with this one. And so 4 is consecutive with 3 and 5, which is not a possibility on these anymore because we removed the 3. So we can remove 4 as a possibility here. So now this is down to 1, 3. We have a 1, 3 pair. And so because we removed the 4 from here, we should remove the 1 from here, because now 1 would have to add with 4 to make 5. So we have 1, 3, and 2, 4. And so next what we can do is we can look at this chain of consecutives. So we can think about what can actually go there. So one of these is going to be a 1, one of these is going to be a 3, just by definition of the pair. So if this, we'll just pick one. Let's say this one's 1. So if this were 1, this would have to be 2, because it can't be 4. It has to be consecutive with 1. And then we have to be consecutive with 2, which is 1 or 3, but we've already used the 1 in this row. So we'd have to go 1, 2, 3. If it were 3, in isolation, there's 2 possibilities. There's 3, 4, 5. That's absolutely possible. But also we could do 3, 2, 1. But I'm not going to mark that, because if we look, if this is 3, this is 1. And we know for 1, it has to be 1, 2, 3. So a 1 here forces a 2 here. So if we have a 3 here, this is 1, 2, 3, putting a 2 here. And so this can't be 3, 2, 1, because then we'd have 2 2s in this column. So these are the only possibilities. We have 1, 2, 3, or 3, 4, 5. And sorry, 1, 2, 3, or 3, 4, 5, but we can't have 3, 2, 1. All right. Or any other weird combination of that. So one thing that we will notice right away with this, but we won't use it yet, is that we actually have an X-wing on 3s in a way, because we're either 1, 2, 3, 3, 4, 5, in which case the 3s are here, or we're 3, 4, 5, 1, 2, 3, in which case the 3s are here. So either the 3s are here or the 3s are here, which means that none of the other rows in this, none of the cells in this row can be a 3. Otherwise, there'd be nowhere to put 3s in this X-wing. All right, so I pointed that out. We'll try to remember it because it'll come in handy later. All right. So the next thing to look at is this group of consecutives. So we can do the same thing. If we start with 1, then we have to go 2, 3. There's no other choice. If we start with 3, we can go 2, 1, or we can go 3, 4, 5. So these are the possibilities for that consecutive. And 3, 4, 5 is absolutely possible here. We don't have the same situation we had in these 2 rows. All right, and so next we're gonna, if you looked at my mouse, I got ahead of myself, but we're gonna look at this area and we're gonna start with this chain of black dots. And the only reason I didn't, it's always good to start with black dot chains because they're limited, but I wanted to fill in this top area first. It doesn't really matter what order you do it though. So this black dot chain is interesting because we can't have 3, 6. So we already can't ever have a 5, 7, or 9 on a black dot because there's no way to divide those by 2 and there's no way to multiply those by 2. So 5, 7, and 9 are not possible. But also when you have a chain of 3 that all see each other, you can't have 3, 6 because you'd go 3, 6, but then what goes here? The only thing that 6 can see is it can have on a black dot is a 3, and that would repeat a 3 in the box, among other issues with this X, right? So in here we have 1, 2, 4, and 8. So we can either go 1, 2, 4, or 1, 2, 4, or we can go 2, 4, 8, or 2, 4, 8. So 1 and 8 actually can't go here. So next what we'll see is we actually have this 1, 3, and 2, 4 pair going on here. So 1, 2, 3, and 4 are used for this column already. So we can't use 1, 2, 3, and 4 in this cell, which actually limits it down to 8. So this is 8. 8 can only go with 4 on a black dot, and 4 can go with 2 or 8, but we already have the 8, so it has to go 8, 4, 2. We filled this 4, so now we can go fill this 2. Now that we know this is 2, it has to be consecutive, so it can't be 5 here. So this is either 1, 2, 3, or 3, 2, 1. And we can't disambiguate that yet, but we will keep working. Now, of course, this 4, I was dealing with it up here, but we can also deal with it here. This is a 6. So, because it has to add to 10. There's only one way to do that. All right, so these two have consecutive values here. So 8 has to be consecutive with 7, 9, and 6 has to be consecutive with 5, 7. And of course, we have the evens done in this box. So the rest of this box would be 1, 3, 5, 7, and 9. And of course, this has to be consecutive with 2. So it's 1 or 3. But these are not limited at the moment. These don't make any kind of triple or anything like that. The other thing we can see is that these are all odd numbers. So if you're consecutive with an odd number, such as this cell, you have to be even. So this is limited to the even numbers. Okay, so next we will look at this area of dots. I guess I should do this X first, actually. So this is 1 or 3, just to fill that X. So we're going to look at these cells to see what this can be. So this cell's values right now basically can't be a 2 because a diagonal with an 8. But everything else is fair game, except we do have to add to 10. So we are limited by what can be here. So we might as well fill in the rest of these 3 cells with the possibilities. And that's going to be 5, 6, 7, 9. And there's no eliminations for that yet. But 5, 6, 7, 9 has to add to 10. So we can be 1, 3, 4, or 5. So that's how you add to 10 with that. But we have a 2, 4 pair here, which means this can't be 4. So that removes 4 and 6 from there, because now we can't. If we remove 4, we have to remove 6, so we can still add to 10. So the next thing that I'm going to be looking at is this X here, this group of 4 cells, and what can actually be in here, because it's much more restricted than you'd initially expect. So I'm going to start with everything that they could possibly be theoretically in a void. So that's everything but 5. And obviously, even though 5 plus 5 is 10, we can't put 2 5s in the same box. So the first thing we'll do is remove this 6, 2. So the 6, 2 gets removed, and that on the other side, the equivalent is 4 and 8. So we remove 4, 8 from there. Second, if you remember, we had this X-wing on 3s. And so that means that these can't be 3, which I explained earlier. And so specifically, these can't be 3. And so then the equivalent 7s on the other side can't be there because, again, we have to add to 10. So next, we're going to audit every number to make sure that it actually has its consecutive buddy. So, for example, 1 here doesn't have its buddy 2 over here, and obviously there's no 0 either. So 1 can only be consecutive with 2, and there's no 2 here. So we can remove 1 and then the 9 from here. And so 2 has 1, 6 has 7, 7 has 8, but 9 and 9 has 8, right? But on the other side, we have 1 with 2, and then 4 doesn't have a 3 or a 5. So we can remove 4, 6. And then the 7 has the 6, the 8 has the 7, but the 9 doesn't have an 8, so we can remove 9, 1. And then if we were to look at these, we'd see that they all actually do have buddies. But next what we'll do is we'll see that this can't be a 6. So if I place a 6 here, and I'm just going to show it because it makes it a little bit easier to see. So if this were a 6 here, that forces a 4 here. And simultaneously, has to be consecutive with 7, so that's 7, 3. But now what can this cell be? It can't be a 3, because there's already a 3 in the box, and it can't be a 1, because a 1 would be diagonal with a 4, adding to 5, and that breaks the negative constraint. So that actually removes all possibilities for this cell. So 6 is not possible here, which means 4 is not possible here. Now we removed this 6, which means now the 7 isn't possible here. So the next thing I'm going to show is that there has to be a 2 here or here, and that's relatively easy to see. So if this is a 2, there is a 2 here or here. The other option is if this is a 9, 9 puts a 1 here, and the 1 has to be consecutive with a 2, so that puts a 2 here. So 2 is here or here. That removes the 2 from this cell. And next we're going to fill in the rest of what this column can be, because we actually have a 1, 3, 8 triple. So this column, we can have a 4, 5, 7, or 9. And additionally, we have a 1, 3, 8 triple in this box, so this can't be 8. And we've limited this down to 4 or 6. So that's going to remove, we can't be 1 because we need a 2. The 3, 5, and 7 can be adjacent to 4 or 6, and then we can remove the 9. And also this 2 here sees this 3, so we can remove the 3. So now we have 3 here or here, might as well mark that. And we have 1 here or here. And 4s are here or here, if you look at where our box candidates. And 6s are here or here. So next we are going to try a 7 here, and very quickly that will also explode. So a 7 here, because of the negative constraint, removes 3 as a possibility on this cell. But the 7 also sees this cell here, forcing a 5 here, and so 5 is also removed from this cell. But we took the place of a 4 corner mark here. So that places the 4, and now what can this be? It has to be consecutive with the 4, but 7's the only possibility left. So this can't be 7. All right, so next I will prove that this cell can't be a 7. So if we put a 7 here, it affects a lot of different cells. So first of all, this has to be 3. That removes the 7, 3 possibility here. This 7 forces this to be 5, and so that places 1, 9 here. So we can remove the 9 possibility and the 5 possibility here, leaving just 4. Additionally, this 7 and 5 remove the 5 and 7. Whoop, remove the 5 and 7 possibility here, forcing a 3 here. But the 6 is the only value left here, and there's a few ways to say this, but this isn't possible. we need a 4 here, but then now what goes here? Or if there's a 6 here, then that's not consecutive. So 7 here forces a contradiction. So we can place 9, 1 here. And that is going to have interesting consequences there. So next we're going to look at this white and black dot. We're going to fill out the possibilities. So 3, 5, just from a consecutive, would have to be 2, 4, or 6. But it can't be a 4 because 4 would be diagonal with 1. So it's actually 2 or 6. And what can the 2 or 6 be with the black dot? Well, 2 can be with 1 or 4, and 6 can be with 3. But we have a 3, 5, 7 triple in this row already. So this actually can't be 3, which means this can't be 6. So that places a 2. 2 has to be consecutive, so that has to be 3. 3 places the 7 here. There's a lot of cleanup to do with this, so that these 7s are removed, making a 5, 6 pair. This 7 sees diagonally here, removing 3 and 7. This 2, 9 pair removes the 9 here, leaving a 4, 5, 6 triple here, so I can remove the corner marks. Also, the 3 we placed sees this cell, removing 3 as a possibility, and that took our corner mark 3, so now this is a 3, and that took corner mark 1, so this is a 1. So we're down to a 5, 7 pair here, 4, 5, 6 here, 1, 8, 2, 9. We can remove the 2s there. So the next thing to see is that putting a 5 here places a 7 here. That much is obvious. But what can this cell be now? So 5 sees this cell, and we can't add to 10, so that removes 5 as a possibility. And obviously this 7 removes the 7, so there's nothing to put there. So this can't be 5. So this is 4, 6, 5. All right, so now we're going to take a look at this box, and we're going to do some whittling again. So let's start with 1, 4, 5, 6, 7, 8, 9, which is what can be in the box. But obviously 1, 6, and 8 can't be in this row, and 3, 2, and 4 can't be in this row. And we have the 3, 5 pair here, so this can't be a 5. And we have the 2, 4 pair here, so this can't be a 4 or a 2. And this 3 is diagonal with this 7, removing the 7. So now both 4 and 9, whichever one we pick, is going to be diagonally adjacent to, or cannot be diagonally adjacent to a 1, because that would either add to 5 or 10. So if we look at these 3 cells, they can't be 1. So that does a few things. One is that places a 4 here. So that places a 9 here. So we can remove 9s and 4s as possibilities. We have a 5-7 pair. So just more cleanup here. This is the only cell that can be a 1. So we're going to actually just place a 1 in there. And then this is down to 6 or 8. Now we can move over to this box and we'll start with the X. So what can actually be here now? Well, I think it's probably best to just start by filling the row. So this is 1, 6, and 8. And this row is going to be 2, 3, and 4. And so if we look at the diagonals, though, they aren't quite compatible. So the 1 needs a 9, and there isn't one. So 1's removed from these. That places this 1. And the 3 needs a 7. Well, there's no 7. So these can't be 3, and that places a 3 here. This 1 diagonally sees this 4. And they can't add to 5, so this has to be the 2. So this is 2, 8, 4, 6. And we might as well fill in what these 3 can be, which is 5, 7, or 9. And the 3 sees the 7, the 1 sees the 9. And this 3 diagonally sees this 7, so we can finally disambiguate this. This is going to be 5 and 7. This 7 sees up to these 2, so these are no longer 7. All right, and we could have done this earlier, but we were having fun at the bottom here. But we have this 1, 8, and that does see this 3. So that places a 3 and a 1, 2, 3, 3, 4, 5. It disambiguates all of that. So if we now look at where 5s can go in row 6, these can't be 5 because there's a 5 in the box. These obviously can't be 5. And this can't be 5 because it would add to 10 with this 5. So 5 is limited to these 2. If we look at where 7s can go in this box, this 3 sees that. This 3 sees that 7. And this 3 sees that 7, as well as there being a 7 in the row. So 7 is limited to these 2 spots. Additionally, this column has a triplet. So 4, 7, 8 in there. And so now these can't be 4, so this is 5, 9. Could have seen that from the placed 4 as well, but just cleaning all that up. And so with this 5, 9, the 5 here also places the 6. So this is just more cleanup from the stuff we did before. I got a little overexcited doing this 3, 2, 4 first, but it all works out, right? So next, this 3 does see these 2 7s, removing them. That leaves just this spot for a 7. Okay, so now we're going to ask, where can 2 and 3 go in this box? Well, 2 and 3 see this column. 2 and 3 see this column. 3 sees this cell, and this can't be a 2 either because it would add to 5 with this 3. So 2 and 3 are actually limited to just these 2. So we can fill in a 2, 3 pair there. But there's a 7 pencil mark cornered. We can remove that, so that places a 7 here. And the 7 actually sees this 3, so we can do 2, 3. So we may as well fill in these 3 candidates here. It's going to be 6, 8, and 9, and this can't be 6 because it would add 10 with the 4. And now really the last thing to look at is this X here. So it can't be 1, 2, 3 on top or 3, 4, 5 on bottom. So we can kind of translate that to being on the top. We can't be 1, 2, 3, 5, 6, 7. So if we can't be 1, 2, 3, 5, 6, or 7, that leaves 4, 8, or 9. And additionally, on the bottom, we could just fill in what the equivalents added to 10 are. So that's going to be 1, 2, and 6. And if you look carefully, you can see that that doesn't get eliminated by those. But this 2 and 6 actually does see up into here. So that places a 1 and a 9. This 1 sees here, so that places 8, 2, 1, 9. and the 9 sees over here, removing 9 as a possibility. And the 8 also sees it, so that places 6. So now we have 8, 9 going on here. We have a 4, 8 pair in this row. So what can these other cells be? Oh, sorry, and then this is a 5, right? 5, 9. So these other 2 cells are going to be 6 and 7. But this sees the 6. So 7, 6. Also, where does a 9 go in here? So this 9 sees this row, this 9 sees this column, and this one sees this cell. Can't be a 9. So that places a 9. And where can 1 go? Well, this one sees this column, this 9 sees this diagonal, and this one sees that. I guess we could have just said these 2 ones see up. So that's a 1 there. And the 7 that we placed here does see down to here, so that's 5 and 7. And we placed this 6 over here a while ago, so that it does see over to here, so that makes this a 2, 8. 8 sees here to make 4 and 8. And really it's just cleanup at this point. So last one for this row is 7. If we look up here, 6 and an 8 here, looking into this box. So this is 6, 8. That leaves 4 and 5. We have this 4, 5, so this has to be 5, 4 like that. We now have a 6, 8 pair in this column, so that places 9, 8, 6, 8, 6, 8. And if we look here, we have this 7, so that places 5, 9, 7. And if we look, this row is 3, 5, and 9 is remaining. The 3 is eliminated from the column as well as the 5, so that has to be 9. And so we can just fill the rest of these rows here. So this is 4, 6, and 8. This is 1, 5, and 4. And this row is 2, 3, and 7. We can just do eliminations. So 7 and 3 are eliminated here. That makes a 2. The 1 is seeing here, as well as the 5. So this is a 4. This should be placeable as an 8. The 6 sees here for 6. The 7 sees up here for 3, 7. This 1 sees 5, 1, 3, 5. And that is how you solve my Diagonal XV puzzle. Hope you enjoyed it. I think it's one of my hardest puzzles for sure. But if you made it through it, congratulations. I think it is absolutely doable. And there's no particular step where there's nothing to try, at least. So you may not see the immediate logic, but just fiddling with the numbers was hopefully fruitful for you. If not, you've got this video to see how to get unstuck. So I don't know why I talk about this stuff at the end when you've already watched the whole thing, but anyway, I hope you enjoyed it. I will put some boxes on the screen for you to see some of my other videos. It's also helpful to subscribe because that way you don't miss any of my videos if you enjoy them. And don't forget to like, leave a comment, all that other good YouTube stuff, and I will see you next time.